Okay.
surprised more people want to hear them.
I know, you sent the email and I was like, wow, that made
I had
me-
people ask, so I was like, got it. Let me send the email right now.
I was gonna ask, and then you sent it, and I was like, perfect.
I was just gonna pray that you were gonna send an email,
Yeah.
so, let's be honest.
Oh, I would have anyways.
Well, she said you were sick, so I wasn't sure if you were actually.
Oh, yeah.
Yeah, it was that too.
I was sick and then I was fine after that. It was literally like a one day, I was like, ugh, but it's fine.
You have like that head cold?
Yes.
Trying.
Yeah, so.
Well, let me just do that. That's fine. That'll be.
I think I have whatever you had.
Yeah, I had it for like the whole weekend last weekend.
Oh, awesome. Alright, so
Ooh.
everyone stay away from me, please.
I'm taking medicine, don't worry. Thank you. It's so kind of me.
Okay. And then I'm trying to think of what else she may have you guys. So we're gonna do this section, and then I'm gonna move into like general things that you should know how to name, because she'll literally have a section where it's just like like draw an alcohol or draw a thiol, and you'll have to know what that is. You don't have to draw a specific one, but
Oh, awesome.
what do you guys need more practice on naming wise for this last one?
Ethers.
Yeah.
Yeah.
Did she teach you guys how to name
Like-
ethers?
Like, no.
Oh.
But like,
Just know
kinda.
that.
Oh, she did in class, like actually.
Like, let me pull up my notes.
Yeah.
Functional groups.
She just told us
they
this.
combine with oxygen.
And then like she
Oh.
told us about epoxide, and then like.
Oh,
this.
no, then you don't need to name. Yeah.
Okay.
I can show you guys how to. Here, we'll do it just in case.
For
Thanks.
naming, I don't know.
We'll do one just in case.
Okay.
Amazing.
All right. I left myself no space to write, but that's okay. So, for starting at this one,
Oh,
which way would you start numbering? Would you start on the left or the right? Left. So we do 1, 2, oh, this one's more disappointing. 3, 4, 5, ooh, 6. I'm gonna have to change all my numbers. I made the gravest mistake. This is the longest chain, so you start up top. And yes, on the exam, she will be giving you ones like this that I specifically drew, and I even tricked myself. She will be giving you trick ones to make sure that you know like the correct order of numbering, whether that be on a ring or on here. So, this is an oct. The ene is on 4. So 4, octene. There, it's 6 chloro, right? So we're doing alphabetical. 3 methyl. And these are connected. And then I'm missing one thing from this name.
Is it trans?
Yeah, so you would write trans in front. And if there were, let's just say 2 double bonds, you would write like 4 trans, comma, 6 trans, whatever, right? It doesn't matter if there's multiple, you just number that and then put the designation next to it. Up
So
for
we
this.
don't have to put a number if it's only one, right?
Yep, you don't have to put a number if there's only one, because it's implied.
Is she expecting, if there's a double bond, is she expecting like trans or cis
Yes.
every time?
So from now on, because you know trans and cis, she
Uh-huh.
will dock you on it.
Okay.
And I will be honest, I know I've missed it a few times. You
Uh-huh.
guys will probably miss it once or twice.
Okay.
She takes off like half a point. It's not going to kill you, but she will be expecting it every time.
Okay.
So now we have this one. This one's really fun. This starts on methyl. This is bromine. And so even though they're all the same way, right, you can number alphabetically. So I'm going to bromine, make that the priority. 2, 3, 4, 5. So I always start at the end of my name, which leaves me no room in the front. But this is a cyclopentane, right? Because there's 5 in there, so that's how it's gonna end. And there's no double bonds or anything, so instead of pentene or pentyne. I don't even think a pentyne can exist. But cyclopentane. We have 1,2 dibromo. Remember the di in front of there. And then we have 3-ethyl. And like I predicted, I'm running out of room for methyl. You don't need any cis or trans or anything, because that's not indicated.
So for numbering, like, when it is all like a halide or or like it's just based off alphabetical order, does it not matter about like what the shortest like?
Oh, it does. It
But
does
so this
matter.
one it didn't, but like in a.
Yeah, so let's just say I added, I don't know. Right? Like you could start, and there's like a big chunk in between here too. Like, so you could start either numbering this way or this way, say it's the same, you always start alphabetical regardless.
Okay, so if it's the same, then you start alphabetical.
Yep, if it's different, like you have, well, you can still start this way,
Mm-hmm.
but, you know. Alphabetical if it's the same either way. This one right here, it's a cyclohexane. Right, so I always start with my ending. I have a methyl and a chlorine. Does not, like, it doesn't matter which one I start on, like, spatial wise, but we're gonna do alphabetical. And so we have chlorine here, methyl here, 1-chloro, 2-methyl, cyclohexane, and then what I'm missing in between is this indication. Is it cis or trans? Cis. So I put cis in front, and that is how you would draw it. Now another way to draw it on a ring, I'll just draw it right next to it, is remember, you can do the wedges. So this would be methyl. That wedge is terrible, don't look at that one. But as long as they're both filled in, or they're both methyl. All of these are cis. So if she were to ask you to draw it and it's on a ring, you can choose either of these ways to draw cis. Mhm.
Show us one of these ways and then access to these transfers.
Most likely, yeah. But she may ask you to draw it, right? If she gives you a drawing section where she gives you the name, you would have to draw this molecule, and you can do it either of these 3 ways. So next up, we have a benzene, right? And you can see what's attached to it. So I labeled this one CH3. I'll label this one CH3 as well. And what is the base name for this called when there's a methyl group on it? The toluene. So what I'm gonna do is I'm gonna name based off the toluene. You guys can do dimethyl if you want, and then have benzene as the ending. But I like to condense it. It's better for remembering too. So if I were to choose where to start numbering, we have something, I mean, these are the 2 ways we can number. 1, 2, 3, 4. And even though you guys can probably tell which way is correct and has lower numbering, we can do the math to check. So if I label this way, there's something on 1, 2, and 4. If I number this way, there's something on 1, 3, and 4. So this way has the lowest numbering. So I'm gonna number, or my substituents are on 1 and 2. Does that trick make sense? So that's how you can check if you're not quite sure, because sometimes with the bigger rings it gets tricky. I am going to erase the trick though. So this methyl could be the toluene. And so you would have 2-ethyl, 4-methyl toluene. And then, for the heck of it, we can name it this way too, so we would have 1, 2 ethyl, my bad, 1,4 dimethyl benzene. So that's the other way.
Can you not name it like a 1,4 toluene?
Toluene itself is just one methyl. Once you add more to it, like it's no longer toluene. That would be toluene plus a methyl group on it. So this one here, what is this group called? Phenol. Right, so this would be at the end. For this purpose, just to remind us, we're going to name it orthometapara, just to review. And so you always start at, this is where we're starting, my numbering. And so then I write ortho, meta, and para down the side. I just write O and P. If you remember ortho, meta, para in that order, that is the way they go. And so you can write them in, and that helps a lot. So knowing this is on meta. So it's meta, propyl, phenol. You guys have any questions about that? And then this one, because you guys asked, as a just in case, if she gives you an ether to name, she's going to expect that you name it by the common name. And so she showed this one, right, which is diethyl ether. And so if this is diethyl ether, because there's 2 ethyls on it, this one is an ethyl here. And 1, 2, 3, propyl here. So this would be ethyl propyl ether. And so that's how you would know how to name them right now. There's other ways to name them. It's more complicated. Yeah.
There's a certain order you put the ethyl propylene.
Alphabetical. Yeah. That's just a good rule of thumb if you don't know which way alphabetical. Do you have a question or are you good? No? You're good. Sorry, don't mind. But do you guys have any questions with naming? I can give more examples. Yeah.
On the left and right as well, would that be unsymmetric and symmetrical?
Oh yeah. This is an unsymmetric ether, and this is symmetric. Yep. So it's super easy to name those. Almost just as easy to name if you just remember to name it by the group. If you guys are good with that, I'm going to erase and just start writing a bunch of, you have a question? Okay. I'm going to start writing a bunch of common names that you should know for the exam because she will have a section in the naming or the drawing to name those compounds or draw one. So I'm going to erase this. And I'm going to put, I actually wanted to classify things. Rats. It's okay. We can classify things really quick. That's so sad. We'll just do it based on this. And I'll add that in just for fun. So, just looking at the molecule here, you can kind of begin to see what she would maybe want you to classify. And so what she's going to do is probably give you a big molecule and tell you to classify the different stuff on it. And so if you were to classify stuff on this molecule, if she says classify a carbon, this is a tertiary carbon. This one right here, secondary carbon, right? What is this one right here? It's nothing, because it's a double bond. So this gets no classification of carbon.
Even though it's connected to the carbon on the 3.
Yep, because it can't be connected to 4 things,
Okay.
right? Because carbon, the way that you number it, is based on how many carbons it's connected to. Let's just draw this, just as a good little, right? It has to be able to get to that quaternary level, and so if it's double bonded, it can't have a classification. So it can't bond 4 times. If we were to classify this alkyl halide, what would it be? Secondary, right? And I'm gonna write secondary RX, because that's the abbreviation she showed you. And remember, R can be any sort of carbon group, and then the X is the halide. And then if we were to do this alcohol, what would this be classified as? Tertiary. Because it's, again, attached to a carbon that has 3 things attached to it. And so when in doubt, all of the things that you have to classify, including carbons, you look at how many carbons are attached to that initial carbon. Now what you're never going to see, let's just make a big molecule, right? You're never gonna see this. Yeah, what's up?
Question, why did you just make tertiary RX?
Oh, this one? So I could do this tertiary, I just didn't write the shorthand for it, but that would be R and then the OH. So something you're never going to see is a quaternary classified like halide or alcohol, because that means that this carbon is bonded 5 times, which is the biggest organic chemistry no-no. So this does not exist. Alcohols, halides, they only go up to 3. A carbon can be bonded to 4 carbons, so that goes up to 4. Yeah.
So like anything, if we could classify anything connected to a carbon, it's the classifications, how many carbons, that carbons?
Attached to. Yep. And so, again, just a reminder, right, if you were to have this is technically an alkyl halide, but this carbon that it's attached to 0 carbons, and so it just becomes like, it's a methyl alkyl halide. I'll just write methyl RX. And so everything is based on that central carbon and how many carbons it's bonded to. And that's not going to be a big part of the exam, but she'll definitely include it in some of the questions. So just remember the carbons if you ever forget. Is everybody good with this? So now I'm just going to write a whole bunch of stuff up on the board with the hopes that you just write them all down or take a picture, because this will basically be the list of everything you need to know. So I'll just start with benzene. And if you can name some of these, then you don't have to wait for me to fill them out. Is there anything else that you guys really need to know for naming? I feel like this is a pretty comprehensive list, but she may have you draw. So this is a phenol, toluene, aniline, thiol, ether, and then an epoxide. Now the reason that I do this is because when I took organic, I remember not memorizing these and having her have that on the exam as draw and then gave me a random one and I was like, so learn from my mistakes. She will recall at least one of these things on the exam. Any other questions? So now we just have, am I good to erase this? Is everybody ready? Yeah. Okay.
Wait.
No, you're good, you're good. Alcohol. So we went over a bunch of different reactions. We're gonna start at combustion. I'm just gonna draw 2 up on the board, random ones. We're gonna solve them. And then from there, we'll do all the different reactions that came after that.
For combustion, do we have that energy as one of the products?
We need to have what?
Energy as one of the products?
No, has she marked it on quizzes? Okay, good. Then no, because she didn't draw it on the board in class. Usually she does, but she didn't this time. And so I've made note of that and I haven't been including it in my session, so I don't think she's expecting it. But I'm just gonna draw 2 random molecules, each with funky little thingies. And then what gets added to it?
2.
2. There's some heat. Or sorry, I should have asked you, what's this symbol? Heat. What's this one? Light. I think that's all you got for now, pretty much.
If she asks us that on the exam, does she want to know is light or Planck's constant?
Oh, light, because that's what, Planck's constant, you don't need to know that. Light is the technical term that she said is fine. So if we're gonna do this, you have your combustion reaction. The first thing you do is you get a molecular formula. So again, alkene, ring, alkyne, okay. So the key to this is that these formulas are really good, but every single time that you add another thing that causes a hydrogen deficiency, you have to subtract by 2. So what I mean by that is this right here, this has 6 carbons, right? So C6, and then what would the normal amount be if it was 2n plus 2? 14. So we know that it has a ring, right? So we can bring that down. That was terrible. Never try to erase red marker with your finger. Right? Since we have a ring, that brings us down to 2n. But we also have a double bond. And so that is going to make it subtract 2 more and have this molecular formula. So every single time you have something that takes away a hydrogen, every time it takes away hydrogens, you subtract that 2. If that was too much and you don't like the formulas, again, you can always count. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's a quick way to count. C6H10. Now I'm going to balance it. So I always balance my carbons first. I need 6 of those. Hydrogens. I need 10 of those. And then to balance my oxygens, what I always do is I simply just count however many hydrogens are on this side. So if there's 6 O2s here, I have 12 oxygens, plus the 5 oxygens from here. So I have 17 oxygens when I go to my bank. Now to get it into O2 over here, I have to divide that by 2. And that's how I get my total amount. Does everybody understand the math that I did with the oxygen tonight? Any questions about this one? And I know I'm moving fast. Thankfully, you guys will have more time tomorrow. You guys will probably finish like around an hour. She doesn't make them super long, but if you do take longer, that's also okay, and use that time as a blessing. Because organic students don't get that extra time. And a lot of them hand in half completed tests. So it's a great time. But is everybody good with this one? Perfect. So I'm gonna refill in this one. And I have I think that's 7. 1, 2, 3, 4, 5, 6, 7 hydrogen or carbons. And I have a triple bond. So I know it's 2n minus 2. So that'd be 14 minus 2, which is 12. So then I go over here. Got 7 here. 6 here. And if I count up all my oxygens, I have 14 on this side, 6 on this side, that equals 20, and I would have 10. So again, I know I moved a little quickly, but if you follow that pattern, it should take you like logistically from step to step. Any questions about this one? I'm gonna pull out my notebook so I don't miss a reaction, because we're gonna move on to all of the other wonderful reactions that you guys learned. If I could find my notebook. I also take notes every single class. I know I've told some of you guys this, but if you ever miss class, you can always ask me for notes if I'm there. I take the same notes that she writes up on the board. So, okay. Am I good to erase this? So what we're first gonna do is look at reactions that involve double bonds and triple bonds, with the exception of polymer reactions. We'll save those for last. But so the reaction ones, I don't give like humongous molecules, right? Because, I mean, she's not gonna give you humongous molecules to react on your exams. But also because, specifically with these reactions, we're only really focusing on the double bond and the triple bonds. Let me do this. So if we have this reaction up here, this reaction, I'm also gonna name all of them, is called hydrogenation. And basically what is happening is you are pumping this molecule with a bunch of hydrogen gas, and you are giving it a metal so it acts as a catalyst to the reaction and allows for a place for the reaction to occur because hydrogen is just too light. So when you see this, this is probably the easiest reaction you will have. It just gets rid of all of the double and triple bonds. Now what does this not? So it does not break a ring, right? It can break the double bond on the ring, but it's not going to break the ring open. And then anything within benzene. So it can break stuff that's on benzene, but benzene itself, it's not touching. So if you were to get a benzene ring and then this, you would just write no reaction. And you would have to write no reaction, because that's technically the answer. But is everybody good with this one? Again, this one, if you see this should be like, yes, easy points. I know what to do. So this one right here, the reason why I did step 1 and step 2 is to show that it works for alkynes and alkenes. And so basically, each step of the way, you are breaking one of these bonds and adding a bromine or a chlorine to the other side. So you could have bromine. And I drew this super weird, so, right, I'm gonna do it both ways. And if I have and the reason why I did it with both chlorine and bromine is that for this reaction, there is no difference between them. When you're adding, this is called halogenation. Yeah, what's up?
Isn't it only when you add like a Fe to it, it substitutes with chlorine? Like in that same reaction?
This? So what you're thinking about is if I wanted to, let's just say, right, if I wanted to add a chlorine to a benzene, this is where you have the iron. And so without this, right, this one has a double bond, so you don't need anything there, or a triple bond. When you're adding to an alkane, that's when you need light. And then if you're adding to benzene, that's when you need iron. So I know it's a lot of stuff to remember, but that would be the pattern for that. So this one you don't need anything, which is super nice. And I'll put this, I'll just like start it, I don't know. I feel bad that it's in the middle, but I don't want to erase it because it's good. And the same applies for bromine, right? It could be Br2 and it's FeBr3. Easy to remember, or not, this part isn't, but if you got it for one, you have it for the other. So this one right here, again, we are breaking that double bond, so I'm just going to draw my shell. And I'm looking at this H and the OH, because the H is going to break off from whatever is attached to, right? In both of these examples that we have coming up. And it's going to add on one side of the double bond versus the other. So the way that you can think about it is that the H is going to join the side with more H's, right? Or that the OH is going to join the higher classified side. So with that logic, if we're adding with the H with the H's are over here. And then the OET, or oops, I moved ahead, the OH is on that higher classified carbon. And so again, what she's looking for out of this reaction is she wants you to draw in that H. She wants you to show the OH and the H being added. And she wants to make sure that they're in the right place. Now for this one, if you look here, each of them has the same amount of hydrogens. Yes.
For like 3 and 4, can we look at it when we have like an acid that it takes away one of the hydrogens from the top of the reaction? So like you have like essentially like an H and O left. And
Yeah.
like down the bottom you can see that you have like an O and a theory or
Yeah, just an H left. Yeah, that's how I think about it. I think about them completely separately. That they're adding completely separately because they're in acid. The acid is what's making them able to split. So, what's it saying? These both have the same amount of H's. Yes, sorry.
Sorry.
No, you're good.
I mentioned it already, but does she want us to show that intermediate step with the step one, or is it okay to just?
Oh, this?
Yeah,
Oh no, you can go straight here.
okay.
I drew this for the example to show that it works with both triple bonds, and then it can also substitute a double bond too.
Try minus one.
I know.
Why is there 2 H's in the second part of that? There was an H there the whole time. Okay.
Yep. Yeah, so I just kept it.
Honestly,
Yeah.
I was like, why is there 2?
I made them friends. Don't worry. We all good? Perfect. So this one here, again, these are both they're not secondary carbons because they are double bonds. But they each only have one hydrogen attached to them. So there is no preference. So you would end up in this case with 2 different products. And she will expect you to know when you only end up with 1 product versus when you may end up with 2. So do you guys understand why that is?
will she tell us if like there's supposed to be like 2?
Possibly.
Okay.
I cannot guarantee that. If you get to this step and you get confused and you're like, both of them have the same amount of H's, I'm just gonna put 1 down, she'll maybe mark half a point off for not listing the other one. But your answer's still correct.
Show us the H's.
No. Like these? No. You gotta draw those in. Which is why I drew these figures like initially without H's, and then as I'm solving the problem, I just draw them in myself. Because that's what helps me keep my head in order. It's like, which side am I adding them to? If I know where all of them are, then it makes it easy. These are the ones from earlier.
Do you have to draw like those extra H's in, or could you have just left it the
No.
H? Okay.
You could have just done that, right? You just want to show the H that was added and then what was added with the H. Any other questions about these? Again, these ones are all related to double and triple bonds. Again, if you really wanted to, let me just, I don't know if I want to make that more confusing. But if this was a triple bond, right, it would add in the same way that these do. What's up?
I was gonna ask, the last one was like an H anything, right?
Yeah, this is an H anything.
Okay.
Both of these are technically H anythings.
Okay.
And so instead of this, the only other example that she's not going to give you other than like an alcohol and water is like maybe hydrobromic acid or hydrochloric acid. So the only other ones you may get are HBr and HCl, but the same rules apply.
So, if it's an H anything, are there still getting multiple products? Because I thought you were supposed to put the H on the side where there's more H's.
Yep. So in this example, there is no side that has more H's.
Okay.
So you're going to have both products. In this example, there is one side that clearly has more H's, right? And that's this side. So you only have one product.
Thank you.
Yeah. Any other questions?
The ETs is ethyl. I mean not ethyl. They're making that one. ET.
Oh, does this make? Oh yeah. like this. Is that what you're asking?
Is that how it should be?
Yes. I just forgot to write it in. Yes. There we go. My bad. And that would be an ether. So if she were to ask you to classify it, but that's what it would be. Do you have a question?
Could you tell there's no hydrogen, well, there isn't, or I'm.
Like on this one, on how many? There's more.
Yeah, how do you tell when there's not, there's
So the thing is you can't, which is why you have to put both. Right? You can't tell which one is the right one. So you put both because it's gonna make both. Neither one is right.
why can't we tell?
Wait, what?
Why can't we tell?
Because both of these, right, each only have one H attached. And so the H is not gonna prefer one side over the other. Because there's the same amount of H's. Since there is no preference, it will add either on this side or on this side. So hopefully when she does this, she'll give you a clear-cut example like this. This was more of a challenge one. But just remember which side it is. Okay. Are we good with that? Perfect. So we're gonna skip over polymers for right now and just do the bromination and chlorination of alkanes, because this one is the one where she will be specifically asking you for a specific amount of products. So I'm just gonna draw I think I made this like way too long for my example, but it's okay. So you may see that I drew the molecule twice and I'm separating chlorine and bromine now, because when they are adding to a single bond, they are going to act differently than what they would with a double bond. They're not going to act in the same way. So with this, what is happening in this is that the bromine and the chlorine are replacing a hydrogen that's somewhere on the molecule. And so with bromine, you're going to look for the highest priority of carbon, and that's what it's going to attach to. So I put this on here to trick you, because I like to, again, I think I did this literally my last SI session, but put this on here to trick you, because it will trick you if you do not remember that this carbon has 4 carbons attached to it. It cannot lose a hydrogen. And so the bromine cannot bind to this one. This one, however, is tertiary and has a hydrogen that can be replaced. And so the bromine will replace it. And there's one product. Now, an example of where there may be more than one product is if it was symmetrical, right? So if you had something like this, you can have a bromine substitute here, or you can have a bromine substitute here, right? They're all secondary carbons. These are technically both stable. This would be 2 results. Does that make sense? So this is when ER2 has 2 products, it's when it's symmetrical. And you can't choose between the H's. So let me just ER2 HB. So typically for these, again, other than the example I just showed, because I don't know what trick she's going to put on there, bromine is probably going to have just 1 product. It should be the highest substitute. Now chlorine, this one is pretty easy as long as you write different products. Because again, remember with symmetry, things could get confusing. You may accidentally write the same molecule, but it's just like reversed. So if I were to do this instead of that and call them different, like those are the same, technically. So you can put a chlorine wherever you want. It doesn't need to be substituted anywhere. Now what we're not going to do is put a chlorine on any of these, because look, right, this is a methyl, this is a methyl, this is a methyl. If you put a chlorine on any of these, it'd be the same. Because any of these could be your one carbon. But you can put one here. You can put one in the same place as you put the bromine, and so on and so forth. There's a bunch of different options. And so she will typically tell you how many products to draw for this one, because sometimes there are so many that you do not know how many to draw. If she does not give a number to draw, that means the molecule is small enough that you can get all of them within maybe like 5. So that's a warning. She may not tell you if it's under 5. If it's more than 5, she'll be like, give me 5. Give me 3. Give me whatever.
She doesn't keep you waiting, you just assume or
You keep going until there's no more.
So
Yeah.
it would be 6 on this one?
1, 2, 3, 4, 5, and then 6. Yep. So there's 6 different places. So again, for this one, I would hope she would give you a number to cap you, because 6 is too many. I've had to draw 5 before, but I'm thinking she'll ask you guys for like 3, because that's what she's been doing in class. So, any other questions with this? So the last thing to go over is polymers. And again, like I warned last time, she's going to ask you about the 2 different types, or she's going to pick one to choose from. Which one did she ask you guys to describe on the quiz?
She didn't ask this.
She didn't. That means it's coming for you. She always has a question about the polymers, whether it be the vulcanization process or whether it be the billiards balls. So, like I did last time, I'm just gonna go and list the things that you need to know. Billiards, rubber. Where's her little spiel? Okay. 20th century contest. And what is the polymer called? Bakelite. And so that, and if she asks you for things to describe it, again, light, but like sturdy, tough. Because pool balls can be hit around, but they're super light. You can toss them up in the air. They're not gonna, I mean, they could shatter a window. Don't throw one through a window. But they wanted something light that was also sturdy and tough. So she may ask just about that. And if she asks what kind of polymer it is, it's a man-made polymer. Now rubber, I don't know if she gave a year for this, but things to remember are Goodyear. Again, the fact that rubber is natural. And then the word to remember is vulcanization. And what she will probably do is if I were her, I'd be like, explain the process in which Goodyear made tires. You can literally draw natural rubber, sulfur, but make sure that you get this drawing right. You want to draw disulfide bridges. So make sure that there's 2 sulfurs in there, because that's what's being built. Disulfide bridges. And this made the naturally soft polymer into something still soft, but less malleable and more sturdy. And so those are the 2 things that you would know for like the open-ended. But the second component of polymers is I'm just going to draw it basically underneath. I'm gonna draw. Let's just draw this. She may give you something like this and tell you to make it into a polymer. And so if she were to tell you to do this, this is my trick. I just write the units twice. No bonds, no nothing. Right? And then I just connect them all with a single bond. No double bonds. Only single bonds. And she will want 2 units. 1, 2. Yeah, what's up?
After it goes through that, will the first part of it keep the double bonds?
Nope.
Okay.
It's all single bond now. Yeah, you're never going to be expected to draw that. I guess the very, very end unit, maybe, right? In theory. Unless they gained a hydrogen on the end. But I've never made a polymer before. So you only need to know this. Now what she may do is give you something crazy like this and say make a polymer out of it. Now this is not as crazy as you think, right? She does this because it throws you off because it's thick and it's really small. But if you break it down, right, there's a carbon here. This is what it looks like. Then you can fill in the hydrogens. So it actually just looks like this. So again, just a warning, she may give you something that looks like in stick form like this, or something very similar. But if it helps you to draw it as a polymer, I recommend redrawing it with the carbons and everything. That way, when you fill in your polymer, it's super easy. Do you guys have any questions about polymers? Yeah.
On the one left, have you CH2 in it?
Oh, yep.
Okay.
Yeah, when I'm writing these fast, like, please stop me. I make simple mistakes all the time. But yeah, CH2, all single bond. And again, this wouldn't be like a super heavily weighted question. This one will be, right? And this should be, you don't have to like memorize it like you would the formulas or anything or the reactions. Like this is just knowledge. So writing a short little blurb should get you full points. Yeah. She'll say whether she wants full sentences or not. If not, assume you don't have to, but give the information, like, again, sturdy, tough, it's a man-made polymer. I would give more information than this. Yes.
And the Bakelite was the polymer that they made, wasn't it?
Mm-hmm. Yep. And so how I would do that is like 20th century contest, trying to design best billiard ball, guy made Bakelite, sturdy, tough, man-made. Those are my 4 bullets. So just like a few more words. This is kind of bare bonesing. She would not be happy with this, but if you add a little more, you'll be good. Yeah.
On the one on the right, why is it not connected to like the 3rd carbon? Like, is it?
What? Oh, it is.
Oh no, so like in the polymer,
Oh. Mm-hmm.
like is it not connected from that 3rd carbon, the next one?
Oh, so you're wondering why it's not like a string?
Or like, yeah, I guess.
So basically, so this is just super weird. This is just how polymers bend.
Mm-hmm.
Like you end up having this unit and then everything gets built around the double bond.
Okay.
So you could have like 50,000 things down here.
Mhm.
The polymer is just going to be repeats of this with the 50,000 things down here forever.
So it's whatever's in between the double bond.
Yeah, the double bond is
And
what
then
matters.
everything goes around it. Okay.
Yeah, the double bond is what you really, really want to focus on. Anything else attached to it just goes underneath.
Okay.
Guys have any other questions? So I'm not gonna, I probably won't give, you guys want practice problems? Because I feel like that's almost,
Could you do like polarity?
oh yeah, polarity. Yeah, I'll just go over it really quick. And no, did you have your hand up?
Yeah, we did practice problems. Like we just take a picture.
Okay, yeah, I can do my best. Ugh. It's just a lot of material, so I don't know what exactly. I can give you guys some naming.
That's really anything to do with anything.
Yeah. Ooh.
So like bond angles good or anything?
Is what?
Bond angles.
Yeah. So we could do that with polarity too. So bond angles, just to review, right? What do you do? Boop. And then we'll do. So here are two molecules for polarity, and again, just to reiterate, this is 109.5. And in both of these, we're going to do bond and molecular polarity because that's what she's going to ask for. She's going to want both. So if it helps for all of these, because it's all about electronegativity, fill in those electrons to help you remember where that negativity is pulling. Because it's not going to pull towards something that doesn't have any electrons. It's going to pull towards the thing that has electrons. So if we look here, there are 3 polar bonds in this molecule. All of them are going towards the nitrogen, right? And so if I were to draw a molecular polarity, it'd be going through that polar side of the molecule. You would not be pointing it towards the nonpolar side. So for molecular polarity, it's not as an exact science as it is with bond, because bond you can put it right next to it. As long as you are clearly showing that the electronegative is over here and that the nonpolar, like the non-electronegative is down here, you'll be fine. So if your arrow is not exact, don't worry, as long as it's clear, right? My arrow head is up here near the nitrogen. The tail is far away from the nitrogen. This one right here, there's only 2 polar bonds. The polarity is going out towards the chlorines, and it's being split equally, and so it'd be going through like that. And sorry my arrows are so dramatic, but yeah, that's how that would go. Any questions about polarity? Sorry I kind of did that one quickly, but. Again, the bond angle stuff and polarity, those will probably be incorporated with other questions, like bigger molecules. Or it'll be draw the dipole on this molecule and classify what's on it, right? So if we were to do this, here's all the dipoles, and then this isn't amine, we don't know how to classify it yet, but we can probably assume, right, this is, well, actually it is classified different. But for the sake of you guys, we'll name it secondary, right? You would have the polarity and then you'd say this is also a secondary amine. But that's not how amines are classified, but you don't need to know how amines are classified. Say it was an alcohol or something. She could ask you to classify it. But any other questions? Because I can try, I'll try and put some practice problems up really quickly. That's just an octagon. Okay.
So wait, for the second one, the number through the bond. So the bond.
Yep, you always have to number 1, 2, or 1, 2.
So this one, we go alphabetical, so we go 1, 2, 3 bromine, and then we go up to.
Yep. I wanted to make it a little trickier. I'm gonna do this. So you have to number all the way around. But, this one, no, because there's no indication of cis or trans. This one, what do you think?
Oh, that makes sense.
Yeah, yeah. I wanted to draw that obviously, so you know, you remember to write cis. I'm not gonna do that. I'm in a ring mood, so there's gonna be tons of rings. There's just like a quick little review of the ones that I think are the most challenging and kind of combine everything.